Welcome back to linear algebra. We're going to jump into Anki to start off with. Do we have any flashcards due? Gotta kill that AC. Or fan. We do have flashcards due. What do we got? What is the definition of a matrix? It's a rectangular array of numerical values, essentially. Rectangular array of numbers. That's so good. What are the elementary row operations on a matrix? How do we miss this, bro? Elementary row operations, you can interchange two rows. You can interchange two rows. You can add one row to another. No. You can interchange two rows. That's the first thing. There's three of them. Second is you can add a the second one is you can multiply a row through by a constant, a non-zero constant, and then the third is you can add one row times a constant to another row. Okay, cool. Good. What are the numbers in the matrix called? Entries. Good. There, we got all the flashcards done. Now we will grade the problems I did yesterday because we are in the practice set for section 1.3. I am very excited still to learn how to do these damn things that I couldn't figure out yesterday. The fucking linear combinations and the row method and column method, right? Yeah, okay. All right, let's do this. I'll be back in a sec. All right, guys, classic math where it actually was way simpler than I made it out to be. The row method has nothing to do with coefficients. I was trying to multiply by coefficients. Nope. You basically, to do the row method, you basically, I think you take the row, whatever row you want to find in the final, yeah, this makes sense. Whatever row you want to find in the final matrix, the product matrix, you're going to take it from the first matrix, and they're going to multiply it through the other matrix, the second matrix. To find the column, do the column method. To find the column of the resulting matrix, the product matrix that you would like, you could take it from the basically take the whole first matrix and you multiply it by the desired column of the resulting matrix. That makes sense because the number of rows from the first column or first matrix, that's going to stay into the product matrix, and the number of columns in the second matrix is going to result in the number of columns in the product matrix. Okay. So row method, column method, a lot more clear today. Second, linear combinations. Yeah, this seems to me, from what I understand, you basically take you partition the first matrix into column vectors, and then you basically are going to have a column vector as the second matrix, or you're going to get it into a column vector, and then you're going to take you're essentially going to take each entry out of the second matrix, which is a column vector, and you're going to put it in front of and times it by every column vector of the first matrix. No, I don't think so. I think it's entry 1 from the second matrix times the first column vector plus entry 2 of the column vector times the second row. Yeah, I don't think you repeat the column vectors. That makes sense to me. We can double check that. Yeah, yep. Because you can partition the second matrix into column vectors too, and then define them as linear combinations like we did here. All right, linear combinations are much clearer than yesterday, but still, you know, kind of vague, but it's all right. We did one problem today. This was basically getting a linear system into the matrix form of AX equals B. I think I did it right. As long as part of the step is transposing the matrix of coefficients, then yeah, I got this, but we'll have to see tomorrow if that's the case. So that's it for today. I'll talk to you guys later. See ya.